Hello. Yeah, it doesn't. Yeah. It's not. They need a chart probably. Somebody they need a chart. I know. Okay, sure. You can use this.
Wire.
Yeah, wireless. It's supposed to. It's supposed to have a wireless capability.
Sure it works.
Here we go. Yeah. Check two. Yeah.
Yeah, great.
Yeah, I think if you turn on the Zoom, the mic, you can actually use this one here. Is here? No, it's from his computer. It's
Hello, Victor Ball. Thank you for registering for Athena Seminar SKKU. You can find information about this meeting below. Athena Seminar SKKU. Date and time. August 3rd, meeting ID
wait for Mill to wait. Wait
to
for
edit.
Mill.
Victor, could you please mute?
Yeah, we can mill him, I think. But anyway, okay.
Welcome to everyone. We're going to get started in
We'll get
a
started.
few seconds here.
Okay, hello everyone. I hope you can hear me well. I know I have quite a few people online. Those together we have more than 20, maybe 30 people in person. So it's surprising because usually we don't see so many people during the summer. It's a very, it's very surprising to me, but which is good. Okay, so it's our great honor, to host this special seminar because today we have a couple of visitors, from SKKU. So they flew over, Pacific, to here and to visit us. Okay, so we are very, very excited. So there are a couple speakers, we'll hear their talks, so the first one is actually Professor Jungwan Ku. Jungwan actually received his dual bachelor degree in computer science and engineering and mechanical and aerospace engineering and a master degree in ECE and CS from Seoul National University. This is the best one in the Korean, and also the PhD from Georgia Tech. And then, during his 7 years research experience with ADD in South Korea, basically for the defense development, and he conducted advanced research on the design and performance analysis on the military wireless sensor networks. And he's now, the associate professor in the Sungkyunkwan University, SKKU, South Korean, where his research focuses on deep learning model compression and also accelerator design for on-device AI, and also low-power image sensor system and multimodal AI processing. And he received the Best Award from SRPD in 2016. By the way, actually today I look at LinkedIn, our former student, Boyoung Kim, he actually received the Best Award from SRPD that today or yesterday. For in IS line, it's about 9 years later. So, Boeing also from Korean too. So, okay, so let's welcome Professor Cole to give a talk. Yeah.
Okay, thank you for the introduction, and thank you, Professor Fan, for kind invitation. I'm really excited and honored to be here to present our research. So for today's talk, I will be presenting our research efforts towards resource-efficient AI through software and hardware co-design. And during our 90-minute session, I will first briefly introduce the introduction to our group's research for about 20 minutes, followed by 3 presentations by other group members. So Oh, okay. Yeah. So for those who are not familiar with our school, I will briefly introduce about the school. So actually, Professor Chan introduced SNU as the best university in Korea, but I believe the best private university in Korea is SKKU, and it's actually famous for its old history. So it was established in 1398, which marks it as a oldest university in Korea. And I believe it's one of the oldest universities in Asia too. And with its very powerful research capabilities, we have been ranked consistently around 70, 80 in CS and EE field. And we are partnering with many good IT companies, especially with Samsung, which is very closely linked partner and sponsor to our school. And I will give you a brief introduction to myself. I did my PhD in Georgia Tech under the supervision of Professor Salvar Mukhopadhyay, where I studied my study with image sensor system design. And later I expanded my research into efficient AI model and hardware design. And during my PhD, I did my internship at Microsoft Research for audio enhancement. And based on my expertise in both hardware and software, I have been working on efficient on-device AI research covering various aspects of the systems, including model compression, data compression, and email computing, etc. And my group consists of around 20 members, where half of them are focusing on software side and the rest have focusing on the hardware side. Oh, this is the previous one. I actually tried to find the photo with Juhong and Jinny as well. I think you can find Juhong here, but not Jinny here. Yeah. They have recently joined the Professor Chan's group, so I'm. Oh yeah, thank you for getting them here. So for today's visit, visit was joined by 4 of the group members, including Dr. John and Johnny Lee and Sang-Heum, who will be presenting their work on model compression and email computing research. So I will start with a brief overview of our group's research. So as you know, there are various types of data, including audio, image, video, and 3D data. And those data should be efficiently captured by the sensor. So the one topic that we are working on is the smart sensor systems, which is integrated AI features. And those data should be processed by deep learning models for various tasks. And the critical goal is to achieve high accuracy, but at the same time, we should make it compact to be processed at the edge devices. And of course, the edge devices should be designed energy efficient using either digital design techniques and emerging in-memory computing techniques. And if we expand this scenario into host platform, we may have to send this data to the host. So we are also looking into the methods that we can compress or represent the data more efficiently. And for a given network, we are also looking into collaborative inference method that can optimally split the network into 2 parts for better efficiency. So this is a whole big picture of our research, and we are working on the software side research as well as some hardware design and also system-wide research topics. So I will briefly introduce each of the topics. So The first one is sensors. So my research on sensors started with this chip, which is already 10 years ago. It's called self-powered image sensor that can be sustained without the battery replacement through the energy harvesting from the sunlight. And based on this experience, I tried to perform integration with the AI capabilities. The one way is the functional way, where you can get feedback from the deep learning model about the, for example, object detection from the scene. Using that feedback, we can control many parameters in the sensor, image sensor, for example, modality and resolutions to better capture the scene for the task network. Another integration would be in a physical way, where we can integrate in a 3D way to stack the image sensor and ADC and memory and logic dies to provide a dedicated path from the image sensor towards the memory and logic. And during my PhD, it was all done by simulation, but now I'm working on a project that actually implement this concept with other universities. And in this design, the analog input signal from image sensor is directly fed into the 3D memory for efficient in-memory computing. And beyond the image sensors, I'm also working on various types of other sensors, including the dynamic vision sensor, or also known as event sensor, that generates outputs where the pixel value changes. In those sensors, in practical, there will be so many events when there's noise or non-ROI objects are moving. So there could be a lot of data that should be read out. So to reduce the readout data, we incorporate in-sensor object detection logic using a simple SNN network to detect objects of interest inside the sensor module. And in that way, we can reduce the readout data and efficiently capture the objects of interest. I have also worked on like flexible sensors and ultrasonic sensors to make them more smart and efficient using AI features. The next topic would be efficient deep learning models. So as you all know, one of the common methods for compressing model would be quantization. But beyond the general quantization, we are trying to make it more adaptive. One aspect would be temporal adaptiveness, where we can adjust the precision of the model online without significant overhead. And another aspect would be spatial adaptiveness, where we assign different precision to different layers. To train such models, training such models will require a lot of overhead because we have to set each bit as a trainable parameter. What we have designed is an efficient method that can train such models more efficiently. And these topics will be covered follow-up presentation, so I will keep it brief here. And another overhead of the quantization model training is calibration and need to train the various model with different precision. So what we have come up with is that using just a few models trained, we can efficiently calibrate other models with different precision. So we don't have to separately train or perform calibration that requires a lot of time. So this topic will be also covered by the follow-up presentation. And the contention overhead is also a serious issue in diffusion models. So here we are trying to figure out the group-wise collaboration where we form groups along with the time as well as the layers and perform calibration in a group instead of calibrating each of them separately. And the machine learning is a kind of a very recent and interesting topic. So because recent generative AI models are very powerful, and sometimes it's used for like privacy violation or even crimes. So let's suppose we have a TTS model here, and with this model and a very short audio prompt of a certain user, this model can generate the voice that exactly sounds like that user. So this user may not want this model to mimic her voice. Then what we can do is to unlearn this model, which means we remove the ability to generate the voice of certain user while maintaining the generation performance for the remaining users. So we have designed the training method for unlearning the TTS model for the first time. And we presented this in ICML this year. And this is also featured in the MI Tech review recently. Moving to other modality, we have been also working on a 3D vision processing for autonomous driving and also hand pose estimation for AR glasses. And we have achieved state-of-the-art performances and presented several top-tier conferences. But achieving higher accuracy is not the only target for on-device AI. We have to also achieve the low power and low latency performance. But optimizing the deep learning models do not be enough. So we have also worked on designing the actual hardware, dedicated hardware for hand pose estimator through the optimization on the model size and optimization on the architecture or circuit aspects. So before we tape out this chip, we have verified its functionality on the FPGA. Yeah, so we do this kind of vertical integration throughout the software and hardware side. The next topic is the in-memory computing, where we have been actively working on. So the concept of IMC is to perform inference or training of the deep neural networks inside the memory array, but to support practical and scalable IMC solution, there are so many issues that should be tackled. For example, we have a limited size of the memory array, and also the array structure is quite fixed, and the cells are not reliable. There are some non-idealities, and there is a limited evaluation platforms. So so far we have tackled such those problems and limitations, and we published several papers. I believe some of them will be also covered by the presentation later. Okay, so I move on to the data compression. And so as you know, the human target compression like JPEG or MPEG, it's mainly targeted for the visual quality to human eyes. But let's suppose there is a machine tasks such as classification or object detection, then the compression should be different from the human target compression. So there has been many task target compression methods, but what we are trying to do is to come up with a single model that can work on both human target and task target compression, or we can even transform the existing human target compression method for task target compression methods. And also the compression can go for 3D scene representation or video representation using emerging techniques like NeRF or Gaussian splitting. So for this field, we have presented several papers in top-tier conferences. So the last topic is the collaborative inference between the edge and cloud platform. So instead of performing the entire inference at the host or edge, we found that splitting the network into two parts and performing earlier part at the edge and the rest part at the host would give us better performance and energy efficiency. So we have been applying this technique to various types of networks so far. So here's the summary of my part. So we have been advancing the efficiency of the on-device AI through holistic system optimization across the software and hardware aspects. And for hardware innovations, we could come up with digital accelerators as well as the analog in-memory computing. And we have been integrating multiple modalities such as audio, video, and 3D capabilities. So I believe we have been working on various and very broad area of the efficient AI. So I believe we can come up with a very active collaboration between our groups in the future. Okay, so I think it concludes my part. So, and I think I can turn it over to Dr. Kang Eun-jeon, and he will introduce his work on model compression and in-memory computing domain. Okay, so yeah, okay.
Yeah, I have one question here. Can go back to the slides regarding compression. Yeah, here, yeah. So it looks like you have wavelets, very for the trace and also this is not a machine learning. It's basically wavelet compressed.
So the main part is the deep learning thing, but we are transforming the input video scene into the wavelet, and then we perform kind of machine learning techniques. Yeah. Yeah, I think you can also get questions at the very end of the presentation. Yeah.
Okay, well, let's move to the next one. So, okay, so the next presenter is Dr. Kang. Dr. Jin is a postdoc researcher in SKU. Of course, from the same group, otherwise like Dr. Ho, and he received his PhD from Hong Kong USC and the supervision of the James and also the Q Zhang, where he developed, the I don't know how to pronounce ICOX, not speaking, okay, last weekend, open source energy harvesting IoT device. The Lexabase Babycan was developed, deployed by over 10 industrial and academic economists, including health environment agencies such as EMIT and OTCIO for smart and usable navigation and public alert application. I think recent research is also on efficient AI systems for power and compute constrained edge devices. One.
Thank you, thank you. My greatest honor and pleasure to be here to presenting my work to Duke community and also to Professor Yuan Chancellor. So the title of my talk is Sustainable Intelligence Everywhere, Co-Designing the Future of Edge Intelligence. I believe co-designing between hardware and software, hardware and AI is really the key to making our intelligence efficient. And I believe that will help to make our AI ecosystem more sustainable and more scalable. Okay, so let's begin. So let me give you a quick introduction of myself. So I was born in Seoul, South Korea, and then I did my bachelor's of engineering and my PhD at Hong Kong University of Science and Technology under the supervision of Professor James Shi and Professor Jun Zhang. And then I came back to Korea doing my postdoc at SKKU. And it's actually quite interesting because I'm doing my postdoc, but at the same time, I'm doing my volunteer service. So there's this very interesting system that where you have a PhD, if you have a PhD degree, you can actually substitute your military service with your postdoc. This is a very good deal considering I have Professor Juanco as my advisor. It's very, very good. Yeah, but my military service is coming to an end very soon, and I'll be able to travel abroad and find jobs abroad. So I'm currently I'm seeking my next step, and my ultimate goal is becoming a faculty, tenure track faculty. Okay, so here's a quick overview of my research journey. At Hong Kong University of Science and Technology, I did research related to sustainable IoT, where I was building energy harvesting IoT hardware and also energy saving and intelligent software. During this time, I realized that AI could really help to make my device more sustainable. So during my postdoc, I shifted my focus a little bit, such that I'm now focusing more towards building efficient AI. In the hardware direction, I'm exploring different techniques related to in-memory computing. And on the software side, I'm currently investigating model compression techniques that can actually give you some flexibility. Okay, so here's a table of contents for today's talk. So I'm going to briefly go over the research topics and research works that I've done in the in-memory computing research. And then I'm going to discuss about the model compression research. And then I'll wrap up the talk with the future works. So here I'm going to be presenting 4 papers on the in-memory computing. So to begin with, I'm sure you guys are quite familiar with this in-memory computing concept, but let me just introduce how this in-memory computing architecture works. So in the in-memory computing, we're considering those analog in-memory computing arrays that's probably using some non-volatile memory, such as VRAM. We basically have all the computation that actually happens inside the memory. Our weights are stored or loaded in the form of resistances or conductances on our memory array, and our inputs are basically fed in terms of in terms of voltages. And basically, based on that applied voltage, the current flows through the bit line, basically doing the matrix vector multiplication operation. And the thing about this in-memory computing architecture is that it is very energy efficient because you don't have to move around your data. And the computation is also happening in the analog domain. So you save a lot of energy going back and forth between analog and digital, right? But then we find that there exist 2 key challenges. The first challenge is that applying model compression technique on these IMC array will not actually give you a direct performance gain on these IMC hardware because of their very unique hardware characteristics. So we try to address this issue by playing around with different mapping technique, tailoring our model compression technique, such as to accommodate for this very unique characteristics of IMC arrays. The second challenge is really the computational unreliability due to analog noise. So even no matter how energy efficient your system is, if the computational results are inaccurate, then it means nothing, right? So we also try to come up with different techniques that can actually improve this computational unreliability. Okay, so let's start with dealing with the model compression techniques. So let's talk about accelerating sparsity on in-memory computing. Accelerating sparsity on in-memory computing is surprisingly challenging. There are mainly 2 ways to do it. The first one is a hardware-based approach, where we have some zero skipping hardware that will just skip the entire row of the IMC array to save some energy. Of course, the drawback is that you will need this extra hardware, and also this does not necessarily lead to a cycle or crossbar area reduction because you're just skipping the rows. Now, the second approach is mapping-based approach. Basically, you prune away some weights, and then you compress your mapping and you map it onto your array. But the problem here is that you will require some multiplexer because now your data flow will be more complicated. So in general, pruning on in-memory computing requires, firstly, some additional hardware peripherals that will help you support the sparsity. The second one is that you need to do structure pruning. You have to get rid of the entire rows to save some energy. So there's some software overhead there as well. So the solution we're proposing is to map the activation onto your IMC array instead of mapping your weight to the IMC array. So traditionally, the way we do it is we map our weights onto the IMC array, and the activations are fed into our IMC array. But what we're proposing is that instead of doing that, we map the activation, we input the weights, then we can start to harness the power of unstructured pruning for our weights. So that will give us a lot of software benefit, but at the same time, we can skip all of these rows. And remember, because we are pruning away the weights, these rows will be zero forever. So they can be we can get a lot of gains there. And we do some techniques to merge different mappings, such as to maximize the array utilization. And we find that this will give us a very significant boost in terms of energy efficiency. So we analyze layer-wise energy and latency for classification tasks. And also we compare our method with main mapping method. And we find that our system can outperform existing ones by a large margin. Okay, moving on, let's talk about a acceleration of rank efficiency or low rank compression for IMC arrays. So before we begin, because I know some of you might be unfamiliar with low rank compression, let me give you guys a brief overview of low rank factorization. So the low rank factorization is basically taking a larger weight matrix and then decomposing it into two smaller matrices. Now, why are we interested in using low rank compression? Because the decompression process of low rank compressed matrix actually only requires matrix vector multiplication. And our IMC is very good at matrix vector multiplication. So that means if we compress our weight matrix using low rank compression, we won't need any extra hardware. We just use IMC to decompress it. So we see that there is a huge benefit here, and we try to combine and integrate low rank compression with IMC architecture. Yeah, but what's the challenge with that? What's the challenge with integrating low rank compression with IMC array? The first thing is the accuracy drop due to information bottleneck. If you guys can see here, actually our column vector R, which is a column vector of this R matrix, is actually encoding all the information in the columns of the weight, versus this L matrix is encoding all the information in the rows of this weight matrix. But remember, this R1 and L1, these guys are vectors of the same dimension. They have same lengths. That means that these L matrices, they need to encode a lot more information because this weight matrix is usually a fat matrix in convolutional networks. So a lot of information was bottlenecked here, and we find that this is one of the major cause of the accuracy drop. So that was the first challenge with using low rank compression. Now, the second challenge is array underutilization. Remember, our weight matrix is now being decomposed into very small matrix, either very skinny or either very fat. And when we map this onto our IMC array, we find that it will generate a lot of idle columns and idle rows. So actually, even if we do the low rank compression, because it will not utilize our array to the maximum, it will actually not give us much of a performance benefit. So as is, we'll get, if we use low rank compression on IMC, it will give us a lower accuracy, but also lower utilization, which means lower throughput, okay? So how do we solve this issue? To solve this issue, we first propose a new technique called group low rank compression, and we do this to address the accuracy drop. So the idea is very simple. We basically want to group our weight into multiple groups before doing the low rank compression. So in this particular example, we actually partition the weight into two groups and then apply low rank compression on it individually. And what this basically does is that we will introduce this additional L2 matrix. And by introducing additional parameters, we can actually get some more performance accuracy boost. But the great thing is this additional L2 matrix can be actually mapped onto the idle rows that we saw before. So in terms of the hardware overhead, there's very little hardware or no hardware overhead at all. So we are getting that accuracy boost for free. Now, the second technique is basically taking care of this idle column. So we make use of something called shift and duplicate kernel mapping, such that we can duplicate this R matrix into the idle columns and foster parallel processing of our sliding windows. So that's basically how we take care of that idle column issue. Of course, when we run experiments on the traditional image classification tasks and compare that with existing pattern pruning baselines, we get a significant accuracy improvement, and we can save energy up to 71% compared to our pattern pruning baselines. So we get some good results there using the low-rank compression. Okay, now let's switch gears a little bit. So previously we were talking about how we can accelerate deep neural networks on IMC array. Now we want to talk about a novel, an emerging learning paradigm, the hyperdimensional computing. So to give you guys a brief background about hyperdimensional computing, hyperdimensional computing basically exploits the linear separability in high-dimensional vectors, and it maps your feature vector into a very high-dimensional vector. And then it learns whatever information, whatever features you want in that high-dimensional space. And because of that, we only need to have two modules, the encoding module and associative memory part. And these guys are just acting like a linear layer. But the problem is that because we are mapping our vector into a very high dimensional space, encoding module and associative memory will be a very fat or very skinny matrix. So we have the same problem as the low rank compression issue, where our matrix dimension does not match the IMC array dimension, and that leads to underutilization of our array. Okay, so to address that, what we basically do is instead of having this kind of very long vectors being mapped onto our array and resulting in underutilization, we actually divide this class vector into multiple subclass. And this will actually help us to use less rows, but still populate those idle columns. So instead of having a very long vector that represents one class, we want to have multiple smaller vectors that jointly represent a single class. And we had some issues here, some challenges. We find that when you're training for this kind of system, our HTC model was highly sensitive to initial conditions. So we had to do some clustering to initialize our model properly. And we also find that our model can be very sensitive to quantization error. So we also try quantization aware learning, such as to ensure our accuracy performance. And compared to existing baselines, we find that our work consistently achieves higher accuracy for the same area or for the same memory footprint. And we can achieve up to 13 times energy efficiency and 13 percentage point improvement in the accuracy. Okay, so enough with accelerating and model compression. Let's talk about how we can mitigate the unlocked non-idealities, which I think is really the bottleneck to scalable deployment of IMC systems. So we're going to talk about, so the technique that I'm going to introduce is called row-column hybrid grouping. We basically try to mitigate the stuck-at-faults using weight representation. And before we actually dive into the details of this technical details, let me briefly introduce two background concepts. So in order to represent our signed weight on those ReRAM array, we use a technique called weight decomposition, where we basically decompose our weight matrix into two parts, positive parts and negative parts, and map them independently to negative array and positive array. And we can basically do the matrix vector multiplication on these arrays independently, and then subtract the output of the decomposed weights to get the final output. Now, what about representing a very high resolution multi-bit weight? So we use technique called column grouping, where we have low precision memory cells that is distributed across multiple columns, and they're grouped together to represent a more high precision weight. So that's another way of representing the weight. Yeah. Okay, so let's now talk about stuck-at faults. So based on our previous example, you can see that we can represent some value of weight, say 19, using two arrays. So we have negative array and positive array. And you can see that these low resolution memory cells are grouped together to represent a higher value of the weight. Now, if the stuck-at fault occurs, what happens is that basically a certain memory cell gets stuck at certain level. So if stuck-at 1 has occurred, then the value of your memory cell, logical value of your memory cell will be stuck at 0. Versus if you have a stuck-at 0, then the value of your memory cell will be stuck at 1. But here we are lucky because we find that these stuck-at faults have not actually affected the value of your weight. So your weight is still 19. So we call this case that faults are masked. But you could also get unlucky, right? So here we have another example where stuck-at 0 and stuck-at 1 has occurred in such a way that it distorts the weight. So in this particular case, we get a value of -9. But if we could adjust the combination of the negative weights and the positive weights smartly, then we can find some combination where these two fault configuration will be basically masked. So we can mitigate those distortions. And this is basically what our baseline or our previous work called fault-free has proposed. Now, to illustrate that more graphically, this is basically what we have. So all of these, so basically, the value of our positive weight is represented on this axis. The value of our negative weights are represented on this axis. And if we follow this diagonal, all of the combinations along this diagonal are those decomposition pairs that represent the value of 19. And you can see that some of them may be affected by SA1, some of them are affected by SA0, but there exists some combination that are not affected. So our goal is to find these combinations, okay? If we find these combinations, then we can mitigate the faults. But what's the issue here? The first issue is the number of decomposition pair is quite limited. So we may not always be able to mitigate those errors. The second issue is that this process of finding the decomposition pair is actually a combinatorial search problem. So the search cost for these pairs is very, very expensive. Indeed, the fault-free paper, they reported 8 hours of compilation time for VGG16 network. So that means whatever, even if the fault-free or this kind of fault masking decomposition pair actually leads to a better robustness, it is not actually scalable to real-world deployment because the compilation time is way too long. And these fault map will be unique to different chips. To address this issue, we propose two solutions. The first solution is row-column hybrid grouping. Key idea is to not just group the columns, but we want to group the rows as well. If we group the rows as well, we are basically adding another layer of redundancy. And this will help us to better mitigate the faults and generate more decomposition pairs. But what's the issue with this? If we have more layer of redundancy, this means larger search space. So that's going to make the compilation overhead problem even worse. To address this issue, we propose a novel compiler pipeline called the ILP-based compiler pipeline. So the key idea is that we want to reformulate this problem of finding the decomposition pair into integer linear programming problems. And we find that when we use this ILP-based compiler pipeline together with row-column hybrid grouping, we can find a lot of trivial solutions. So that will actually contribute a lot to improving the compilation overhead. So our key observations that really motivate this work is as follows. We find that fault errors can be classified into just two types. It's either going to be a clipping error when at least one fault exists, or it's going to be an inconsecutive error when fault exists in the cells of the same significance. So as shown in these figures here. Clipping error is basically referring to the fact that you can represent all the weights within a certain range, but if you go outside the range, then they cannot be represented. But then if the weight you want to represent is in these clipped region, then your solution is so trivial because you just need to map it to the maximum or minimum value of your representable range. And we find that this is very, very powerful in accelerating our compilation time. Versus for the inconsecutive error, we couldn't exactly find the trivial solution. So whenever this inconsecutivity error occurs, we'll basically use the ILP formulation to minimize default error. And the great thing is when we start to use the row column hybrid grouping, inconsecutivity error almost never occurs. So it will be most of the error will be from the clipping error, and we'll be able to find trivial solutions very easily for this case. So that's very beneficial. So here is our proposed compilation pipeline. So the first thing is we will check whether the given fault map will have the clipping error. If it does have the clipping error, then we can find the trivial solution. If it does not suffer from the clipping error, then we move on to check if it is consecutive or not. And depending on whether it is consecutive or not, we will use different algorithms to identify the best decomposition pair. So here is the results. We have done our evaluations on image classification tests and also on language models. We can see that our proposed row column hybrid grouping, which is these one, R2C2, R2C4, and R1C4 is basically representing the column grouping method. We can see that we achieve significantly better accuracy and perplexity on both of these tasks. We also made evaluations on the compilation time. So compared to the original fault-free, we can achieve up to 153 times of compilation time boost, mostly because we were able to identify those trivial solutions that were very, very easy to compute. And not only that, when we run our energy evaluations, we find that our proposed method will also give some energy boost. Mainly because in many cases, these IMC arrays, they will have some idle rows. And when we start using row column hybrid grouping, we can actually utilize these rows better. So actually that also helps to save some energy. Okay, that's pretty much it for the IMC topics. So let's switch gears now and talk about model compression. So the type of the quantization, so we'll be mainly focusing on quantization techniques, and we are specifically interested in multi-precision quantization or mixed precision quantization. So unlike uniform quantization, mixed precision, you have spatial adaptiveness. Different layers will have different precision. On the other hand, multi-precision quantization, we basically want to promote temporal adaptiveness, where our model's precision will switch over time. Now, what is the challenge with building these kind of multi-precision or mixed precision quantization networks? The first thing is that the training cost is very high. So we have to be able to accelerate the training of these models. And the second thing is that even if we build these models, we find that they are often very inefficient to be accelerated at inference time. So they may be efficient on the software side, but when you actually load it onto the hardware, it will not work. So we find that there are these two issues. One is the training overhead, one is the inference overhead. So we will be trying to address this issue. Okay, so let's begin with multi-bit precision quantization. So traditionally, when we have a compressed model or quantized model, let's say our model is quantized to 8-bit, our model compression will be rigid, meaning that if you quantize your model to 8-bit, you're supposed to run it at 8-bit. You're not supposed to make it suddenly operate at 4-bit and expect it to work well, right? Multi-bit precision, basically, we want to build a model that will operate optimally for different precisions. So this is basically what the multi-bit precision network might look like. It will have a parent model, which will be like FP32 weight that is being shared by all the child models. And basically you generate your child models by quantizing your FP parent model to a given precision. And we train this network in such a way that it is those child models of different precisions are actually quite optimal. And the way we do that is by actually doing multiple forward and backward propagation for different precision. Then you will allow your model to actually converge to some local optima that actually works well for all the different precision. But as you can see, this is a very, very costly process. So how do we address this issue? So traditionally, our baseline any precision network will have three major issues. The first one is that it will have dedicated batch norm layer, which needs to be trained for all different precision. And second, it will also have a calibration process to support and extend its precision support. And lastly, it will require full data set of forward and backward for each of the precision. Now, our proposed method, which is actually a paper currently under review, we promote shared batch norm layer and also batch norm adaptation, which does not require training of your batch norm layer, but just the tuning of running mean and variance. So that helps to save a lot of the cost in terms of your batch norm training. But at the same time, we also propose a novel technique, which is actually core set sampling. So what we observe is that when we train these kind of multi-bit precision network, we don't need to run forward and backward pass with the entire data set. Because our parent model is shared, if we train a certain precision with a small amount of data, actually this training signal will be transferred to all the other precision. So other precision will benefit from training of certain precision. So we decided to actually sample our data set and only do the forward and backward pass of a small proportion of the data set. And we find that this is extremely effective. We can retain our accuracy to a very high degree, but at the same time, cut the training cost a lot. So here is a quick results. So we can see that here, this is our method. This is the existing methods. We can see that we achieve more or less a similar level of accuracy, but our training time is almost accelerated by almost 6 times. So that is a big improvement. And because our training time is so fast, so much faster, we can not only support those smaller resonant model, but also support larger models such as VITs. Now we know how to train our multi-bit precision network. How do we actually use it in the inference time? So let's talk about that. So if you want to switch precision during runtime, the easiest thing we can do is to actually just have multiple integer models. And you will basically load these integer models depending on your requirement. Of course, we could use something like what I've shown before, using a multi-precision network, such as any precision quantization, where we have a single floating point model on your off-chip global memory, and you just load this floating point model every time you want to switch precision. But of course, this will require very frequent memory access. But at the same time, you need to run expensive floating point quantization function. So the precision switching will be quite costly. Now, to address this issue, what we propose is that instead of having a single floating point parent model, we want to have a single integer parent model. And then we can just truncate the LSB of this integer parent model to achieve a lower precision operation of our network. So instead of having the 32-bit floating point parent model, we have 8-bit floating point, 8-bit integer model, which also helps to reduce the memory footprint. And we just load this 8-bit model and we truncate this LSB to gain the lower precision model. So this will also help to reduce the memory access. Now, but what's the challenge? The challenge is that we find quantization via truncation. Using truncation to actually go from higher precision weight to lower precision weight requires a very special quantizer. So here we have a round to nearest, or also known as Dora-Fogg quantizer. And we find that these kind of traditional quantizers, MSBs cannot be shared between different precisions. And to give you a quick example, suppose we have a weight value of 0.81, which falls in this MSB not shared region. If you were to quantize this weight to 3-bit, it will have the value of 110. If you were to quantize this weight to 2-bit, it will have the value of 1, 0. Now you can see that if we quantize our weight to 3-bit and then truncate it to 2-bit, it will have the value of 1, 1. So there's that discrepancy between doing quantization and then truncation versus directly quantizing our weight to 2-bit. And we find that this discrepancy is enough to actually destroy your model if you do truncation multiple times. So how do we address this issue? Our insight is very simple. We just need to ensure that all the MSBs are shared, and we do that by aligning our quantization bins. And instead of using these rounding functions, as in the round to nearest alpha, if we use flooring function, we find that our quantization bin widths will be uniform for all of the bin width, all of the quantization bins, and this will actually enable all of the MSBs to be shared. And this leads to a pretty good result. Here, the red line is our work using trunk quantizer, and this gray line is showing round to nearest quantizer. So you can see that if we try to truncate, do the quantization via truncation with the round to nearest, we'll see a very sharp drop in the accuracy as we approach, starting from 4-bit, and it's hitting its low at 2-bit. Versus our proposed trunk quantizer will retain a very high level of accuracy. We also do evaluations in terms of memory and energy efficiency. We find our memory storage can be saved up to like 3.5 times. And in terms of precision switching energy consumption, we can almost save it by half compared to the traditional, using the traditional round to nearest or traditional any precision network. Okay, so now let's talk about mixed precision quantization. Actually, this is a joint work with Professor Hwan-Ri Yang from Arizona, University of Arizona. So in mixed precision quantization, the challenge was to find the optimal bit scheme. Finding the optimal bit scheme is a big challenge because this is a combinatorial problem. You have to search for that optimal bit scheme. And one way of relaxing this combinatorial problem into a continuous problem is through a technique called bit sparsification quantization. In bit sparsification quantization, basically what you do is you take your weight parameter, say it will be quantized to 8-bit, then you split this weight parameter into 8 different parameters, where each of this individual parameter is representing a bit of your weight. And then you can apply your sparsity inducing regularization on these individual bit splitted parameters. And you let it go to 0. And once they are sparse enough, you can prune, and they will have the same effect as having a mixed precision quantization. But what's the problem with that? Previously, we had 1 parameter, but after the bit splitting, we have 8 parameter. So there is the GPU memory overhead. To address this issue, we propose a novel technique where we are not doing the bit splitting, but we are just extracting the least significant bit and then adding regularization on top of that. And the way we extract the LSB is by taking the difference between a higher precision weight and the lower precision weight. Once the LSB is extracted, we can apply some regularization such as L1 norm and add that to the loss, and then we can do the backward and forward to make our LSB go to 0. Now, but what's the challenge with that? It's very similar to trunk quant. We find that LSB extraction and regularization also requires a special quantizer design. And the reason is because using the traditional round to nearest quantizer, the LSBs cannot be properly extracted. And we also find that these regularization gradients are often one-sided, leading to slower convergence. So we wanted to use both sides of the gradients when we are actually regularizing for these LSBs. So here we propose our novel quantizer, which is called round clamp quantizer. And here we had to do something different from trunk quant. In trunk quant, we had to align all the quantization bins to ensure that MSBs are shared. But here, we want to make these gradient bidirectional on both sides. So to achieve that, we had to deliberately slightly misalign our quantization bins. If we slightly misalign the quantization bins, the LSB that we extract will be either +1, -1, or 0, allowing our L1 regularization to be more effective. So we test this on various networks. You can see that in many cases, with the traditional bit sparsification quantization methods, we will reach out of memory at very small batch sizes. But with our proposed method, MSQ, we can use a much larger batch sizes, leading to almost up to 81% reduction in training time. So that is a very significant boost. We also evaluate its accuracy. We find that its accuracy, we can achieve, our MSQ can achieve higher compression rate on both ResNets and VITs. And also we can achieve similar or better accuracy at these high compression rates. So these are some very promising results. Okay, so that's pretty much it for the model compression. Now I would like to conclude my talk with some future works. So for future works of related to robust and efficient IMC systems, my research has been focusing on accelerating models in IMC array, either via sparsity and rank deficiency, and also on emerging computing paradigms. And I was focusing on mitigating non-ideality such as stuck at faults. Now, what's the limitation of my current research? We often focus on single model compression technique, not combining multiple model compression technique together. And also our research on non-ideality mitigation is not applicable to various types of variations, but limited to just stuck at faults. So in the future direction, I would like to address this limitation by exploring combining multiple compression technique and building novel technique that will enable robustness against analog variations. Now, what about the future work on multi-bit quantization, on generative, on multi-bit quantization? So my current limitations is that our research on multi-bit quantization is limited to discriminative models and is limited to training-based models. So it's not scalable to larger models or to those generative AIs. So my future direction is that we want to adopt multi-bit quantization onto those larger models. And to this end, we have to come up with post-training method for multi-bit quantization. And ultimately, what I would like to achieve is precision switching across temporal axis. So for LLMs, they'll be changing the precision of the model per token. For diffusion models, they'll be changing the precision of the model per time step. So that's pretty much it. Thank you for listening. And if you have any questions, I'll be happy to answer them. Thank you.
I think we have a
Yes, you want to take a 1 minute break?
No, I think I'll go break, yeah, a minute break. So, yeah, so we can, guys, refresh yourself with drink or something. Yeah, and then we can start. Cookie or something, just grab one. Coffee, just coffee yourself, please. Oh, yeah, it's only 5 minutes. So I can talk to you when I live. I don't think we have the really effective or with the leads that will get then cookie or coffee or anything. Okay, so we'll continue. The next talk will be given by Johnny. How to pronounce Lee. Johnny Lee.
Yeah,
okay.
thank you.
So Johnny received his bachelor degree in electrical engineering from SKKU in 2019, where he currently pursued his PhD in the UCE. It's a research interest in deep learning acceleration and efficient CNN, CNN mapping to mapping aware tooling in inner computing architecture. So, yeah, please.
Thank you, Aaron. Yeah. Thank you, Professor. And hello, everyone. My name is Johnny Lee, PhD student at Sungin University in South Korea. Today, I'd like to introduce my work titled Optimizing Weight Mapping for Energy Efficient in Memory DNA Inference. Before starting, I will briefly introduce myself. I joined the IRIS Lab in 2019, and I have studied research with in the IRIS Lab with Professor Cole. And the research interest, my research interest is mapping optimization for energy efficient IMC-based DNA inference, including optimal mapping and mapping aware weight pruning. Let's start. CNN have been widely used across the various fields. One of them, CNN, have used for image classification to extract meaningful features from data using filters. Transformer with their attention mechanism have been adopted in models like VIT or for classification and in LLMs for generative tasks. However, under the traditional von Neumann computing architecture, the real-time inference of DNNs faced significant challenges like high energy consumption and then high latency due to the substantial data movement between the processor and memory. To address this issue, recent studies have explored the in-memory computing architectures, which can reduce the data movement by performing the computation in the memory. In addition, these architectures are optimized for the matrix vector multiplication, enabling highly parallel computation. However, computation resource available within the IMC array are often insufficient to map all parameters of DNN directly onto the array. Therefore, two key challenges arise. First, how to transform convolution and attention operations into a form or suite of for MVM-based computation. And second, how to efficiently map them onto the array to minimize the energy consumption and improve the inference latency. In this chapter, I will introduce techniques for efficient CNN mapping. As I mentioned at previous slide, CNNs have been used for image classification. And one of the key characteristics for CNN is filter use when extracting the features from input data. In other words, the values of filters remains fixed during inference. Because of this property, many studies have been adopted weight stationary mapping, where the weights are mapped onto the array and remain in place during computation. Prior works used basic mapping method without the consideration of array or convolutional array layer size. This often leads to low utilization and need for the conditional arrays. To address this limitation, we propose an efficient mapping method that better matches the convolutional layer to the available array resource. While this approach improves utilization, it still leaves some memory cells underutilized, which lead to unnecessary energy consumption. Finally, to further optimize the energy efficiency, we combined efficient mapping and mapping aware pruning, which enable more efficient CNN inference on IMC systems. So the goal of this chapter is to achieve multi-level mapping optimization through array and row and cell level tunings for faster and efficient IMC-based CNN inference. So first, I will introduce array level pruning for energy efficient weight mapping. Recently, several mapping techniques have been proposed. However, depending on the size of the convolutional layer and the array, some arrays may suffer from low utilization. To address this issue in this work, we aim to remove some weights that cause underutilization, resulting in reducing computing cycles. I will introduce the recent weight stationary mapping method. One of them, the image to column called IM to core method is commonly used in mapping techniques. In this method, 3D kernel is or mapped to columns, while the corresponding input data recovery window is loaded into the rows, enabling this array to perform MVM. However, one major drawback is that it can lead unused memory cells, especially when there is mismatch between the array size or convolutional array layer size. To address this issue, prior work proposed shift and triplet kernel method. This technique used a larger window that include more input data than IM core, and it mapped the same kernel multiple times across the different column. As a result, the array can compute multiple outputs within a single cycle using different input data. Compared to IM core, SDK better utilized memory cells and reduce total number of computing cycles. However, it increased the size of the weight matrix to be mapped, which may require a larger array size. To overcome this limitation, we proposed a novel mapping method called VWSDK. And this approach use channel tiling for flexibly adjusting the window size to fit the weight matrix to the array dimensions. By applying channel tiling, the weight matrix can be mapped to fit within a given array. However, depending on the channel tiling size, some memory cells may remain unused due to the small number of remaining channels. We refer to those as a residual channel. To address this inefficiency, we prune the residual channels to reduce unnecessary resource use and minimize the number of computing cycles. Experimental results show that this pruning approach reduces the required computing cycles across all convolutional layers, achieving up to 1.38 times speed up compared to the original. Second, I will introduce low-level pruning for low-efficient weight mapping. Weight stationary mapping techniques like IM core and SDK unrolls the weight matrix and resulting in row-wise matrix structure. Recently, some studies have proposed a method to compress the row of IM core-based weight matrix using pattern-based pruning. However, these existing pruning patterns are difficult to apply to SDK mapping. To address this challenge, in this chapter, we propose a pattern pruning method optimized for the SDK mapping, aiming to achieve low-efficient SDK mapping that reduces the low dimension. This figure compares the number of row computation that can be skipped after applying pruning patterns. These red hashed box indicate the weight pruned to 0, and the red line shows the skipped rows refer to row skipping. In IM core mapping, the weights are with the same index share or row. So pattern pruning can remove the entire weight in the row, enabling row skipping. In contrast, SDK mapping has irregular weighted placement, so pruning patterns rarely remove weights in a row. As a result, even with the pruned weight, row skipping cannot achieve. To address this, we propose pairs which designs the patterns tailored for the SDK mapping that maximize the row skipping. With an n entry pattern where n is the number of non-zero values in the pattern, these patterns ensure the removal of entire weights in the rows when SDK mapping is used. Another motivation our work is that prior studies commonly use the layer-wise pattern. This means that the same pruning pattern is applied identically to all corners within a layer. However, this approach has two major limitations. First, it does not sufficiently consider the importance of the weight, which can lead accuracy loss. Second, the row skipping level is limited since the same pattern is used. And we observed that each input channel is mapped independently in existing mapping method. So we proposed Garros, which applies SDK optimized patterns in a channel-wise pattern, distributing the most suitable pattern to each input channel. So for instance, channels with more important weight are given higher entry patterns, while less critical ones receive the low entry patterns. This approach preserves the essential weight while enabling diverse low skipping level. So experimental result in LessonNet 50 on ImageNet and wider LessonNet on Cypher 100 shows that Garros improves the inference accuracy up to plus 4.30% compared to prior works. Last, I will introduce cell level pruning for optimal weight mapping and accurate inference. And pattern-based pruning, including pairs, provide the SDK optimized the pattern-based pruning method. However, prior works, including pairs or Garros, lead to accuracy loss by unnecessary weight pruning. To address this challenge in this chapter, we propose cell level pruning for minimal weight pruning to achieve both efficient mapping and high accuracy. And pattern-based pruning is one of the most powerful methods for row skippings. However, in SDK mapping, the same corner is mapped multiple times across different columns. So applying these patterns can unintentionally remove the weight from the memory cell because they are the same weights. So this leads to our motivations. How can we prevent these weights from being pruned? And it is possible to prune only the weight mapped to the specific cells we target. To solve this, we propose a corner shape control called control. A key feature of a control is the use column dependent mask, which means that each column has its own unique mask. If we want to skip the first row, we can apply the mask only to column 1, so that even though the corners are the same, only the weight element A in the first column set to be 0. In this way, we can achieve the row skipping via cell level pruning while preserving necessary weight. Therefore, control method enables the pruning of weights only in specific memory cells. And however, there is still unused memory cells like this. So to address this, we propose a control with compensatory weights named control C. In this method, we introduced the concept of compensatory weights, placing the additional weights into the unused memory cells. So the basic operation is the same with prior work, but the only difference is that there is a compensatory weight or not. This can increase utilization up to 100% and minimize the inference accuracy loss caused by cell level pruning. And experimental result shows that the proposed control methods achieve higher accuracy compared to the pattern-based pruning method. In this figure, the percentage is a threshold to manage the low skipping level in control method. See the gap between pattern-based pruning and control method. Even with a similar number of skipped rows, control outperforms the pattern-based pruning by up to plus 5% of accuracy in YLSNet 16.4. Notably, control C achieves higher accuracy than this control M, indicating that compensatory weights effectively offset the accuracy loss caused by cell level pruning. So in this chapter, we explored the multi-level mapping optimization through array, row, and cell level pruning for faster and efficient IMC-based CNN inference. And this work underscores the innovative mapping solution and computational efficiency and resource constraint in IMC architectures. So, and next, as I plan to extend my research towards LLMs, so I have been working on efficient transformer attention mapping as a foundation for that direction. In this chapter, I briefly introduce this work. With their attention mechanism, transformers are widely used in vision transformer for classification and in large language models for generative tasks. Recently, many IMC studies have begun to explore how to efficiently map the complex attention operation of transformer onto the IMC arrays. However, unlike CNNs, transform requires complex handling of attention metrics or dynamic data flows or intermediate results. So in this chapter, I will introduce a technique for efficient transform mapping, aiming to optimize the data flow and improve performance in IMC-based systems. There is 3 existing attention mapping techniques. Let me briefly explain each of them. First, REBERT. This is a most basic form of attention mapping where all trained weights are mapped, preloaded, and attention computation are performed sequentially. A major drawback of this approach is the compute dependency. No computation can be performed during the memory write operation to save the intermediate result transpose K and MV. And computation must proceed serially after the write operation. And next, retransformer. To mitigate this dependency in REBERT, retransformer decompose weight metrics so that attention computation can be performed without the transposed K and V. In use only one intermediate result, transposed X, reducing the number of write operation by half compared to the REBERT. However, this is possible only under the assumption that the hardware can compute with both transposed X or X directly. It means that this method requires the hardware support. Without such hardware support, both transposed X and X must be stored in somewhere, making the number of write operations is the same as the REBERT. Furthermore, the compute dependency is not completely solved. Finally, CPSAA, this method pre-computed weight Q and transposed weight K to form the weight S, enabling the parallel computation and resolving the CWC dependency. As a result, it can improve the latency. However, there is a big issue. Please see this mathematical dimension. And the size of weight S grows quadratically with the model dimension, meaning that weight S can be much larger than weight Q and or weight K. As a result, in this increased number of arrays required to map weight S. Therefore, to overcome these limitations of prior works, more efficient attention mapping method is required. So to address this issue, we propose an efficient attention mapping called ETA. ETA preload the weight Q and transpose the weight K, like lead transformer, but write the value not X, and change the order the computation blocks. Therefore, ETA can optimize performance by adjusting the data flow between the computation and write blocks. This approach has two main advantages. First, without the need to pre-compute and store weight as ETA can improve the latency. Second, it can effectively mitigate the CWC dependency through the parallel computation. Furthermore, we proposed an array of aware ETA, which maps the weight Q and weight V onto the same array, since both compute with the same input data X. This allows X to be reused during the inference, reducing the redundant data movement, and we can remove the one computation block. As a result, it enables faster and more energy efficient data flow for attention operation in IMC systems. The left figure compares the latency as the value of alpha increase and where the latency is normalized to ETA. And here, alpha is defined as the ratio between the write latency and computation latency. We vary alpha because memory devices, including more RAM and other RAM devices, shows the different compute to write latency ratio. So we want to evaluate the performance in various cases. As shown in this result, ETA improved the latency up to 20% compared to the Libert and retransformer. And the right figure compares the number of arrays required to map an attention layer with the value are normalized to ETA. Compared to the other method, ETA reduces the required number of arrays by up to 29%. In this chapter, we explore the efficient transformer attention mapping for efficient inference in IMC architectures. We believe these techniques will serve as a stepping stone for expanding our research to LLMs. To conclude, this work aims to enable energy efficient DNA inference on IMC architectures. We have shown that efficient mapping techniques for both CNN and transformer can bridge the gap between the AI model complexity and IMC hardware limitations. And we believe this research paved the way for more general hardware and software co-design frameworks, and we look forward to exploring novel architectures and workflows in collaboration with the broader research community. Thank you. Any other questions?
Finish the last one, we can have
Okay.
the Q&A. Yeah, so the last one from SKU will be presented by Sang-Hyun Yong. Sang-Hyun received a bachelor degree in electrical engineering from SKU in 2023, where he's also currently pursuing his PhD in semiconductor convergence engineering. His current research interests include model compression through quantization and in-memory computing for efficient PEM circuits and the source constraints. Okay, let's welcome something we give talk.
Hello, and thank you for joining this seminar. My name is Sang Hyun, and today I would like to talk about my research regarding hardware software co-design for efficient computing for AI. First, I introduce myself. I'm graduated from the Department of Electrical and Computer Engineering at Sungkyunkwan University, and I'm currently enrolled in the Integrated Master and PhD program at the Irish. And my current research focuses on model compression through quantization and in-memory computing for efficient DNA and accelerator under resource constraints. Before introducing my research, I would like to highlight how much computation is required in deep neural networks. Over the past 2 decades, the interest in improving machine learning performance has grown explosively. One of the main reasons for this is the increasing complexity and size of the data sets. As a result, it has been shown that adding more layers to neural networks actually improve performance. In CNN, for example, lesson 152 has more than 60 million parameters and require about 11.5 gigaflops of computation due to the convolution operations. This trend leads to even greater challenges in transformer-based architecture like LLMs. For instance, GPT-3 contains over 175 billion parameters, which requires a large amount of the memory just for storing the weights. Moreover, to perform attention and fit-for network computation, the model demands about 750 teraflops worth of matrix vector and matrix-matrix multiplications. This means that multiplication are expensive computation due to the massive model size. To address these energy challenges by high computation demand, I conducted research on encoding optimization through quantization, taking into account the hardware design of the processing memory-based DNA accelerators. Before going to the detail, the research assumed an analog in-memory computing system where the multiplications of input and weight is performed inside the crossbar arrays, as shown in this figure. In this fixed system, each input loss is multiplied with the weight columns, and the results are accumulated at the current. To convert the analog current into the digital signals, as ADCs are essential in this system. However, as shown in this table, high-resolution ADCs occupy 31% of the total chip area and consume about 58% of the system energy, making it critical to address this issue. As a solution to the ADC resolution problem, the paper proposed a new encoding method using a center plus offset structure through the arithmetic reforming. In this approach, the center value of the weight is computed by a digital processor, while the offset is computed in an analog domain. This effectively narrows the distribution of the accumulated current going into the ADC, so required ADC resolution can be minimized. However, we have identified several areas for improvement in this encoding method. First, since the center value is determined solely based on the weight value after quantization, it is not a data aware, which means it does not directly lead to a reduction in the actual ADC input values. Moreover, center optimization performed after quantization is constrained by the representation limit of the set, requiring the center value itself to be quantized, thereby reducing flexibility. Second, an optimal center and center value can vary depending on the target IDC precision. In this point, our research is motivated by the idea that center value can be learned jointly with training to better reflect the distribution of an IDC input. So our method integrated the center value directly into the quantization process, which allows it to be treated as a full precision and learnable parameters during training. This integration removed the integer constraint imposed by the conventional post-quantization reforming and enable gradient-based optimization of the center value alongside the model weights. Moreover, importantly, we flexibly incorporate ADC quantization behavior into the training objective. So the learnable center is not only aligned with the weighted distribution, but also optimized to reduce quantization error under target ADC resolution. But there are several challenges arise. The first challenge is at what guarantee should be center be defined. In this figure, channels represent the logical value that appears by one corner. Filters, on the other hand, refer to the group column that corresponds to multiple dot product operation within the crossbar. Since the target architecture is pin-based accelerator, where the computation occurs columnized in crossbar, we choose a filterwise center for aligning with this structure. In addition, while a column represents as a value on which physical operations are performed in the crossbar, we believe there is no substantial benefit during the training phase from using a columnized approach, since columnized value can be derived by bit splitting at filterwise values. Moreover, in practice, weights in crossbar are implemented using SRAM or RM device, and 1 bit or 2 bit per cell devices are typically used due to the reliability concerns. This means the high precision quantized weight must be sliced across multiple columns to be represented. When this slicing is considered during training, modular operations which are non-differentiable are required for each slice, making backpropagation invisible. To overcome this, we parameterize the filterwise center and combining it with ADC modeling, enabling the training process to be optimized for target ADC precision. As a result, we are able to make ADC input distribution closer to zero and successfully reduce the quantization error introduced by the ADC and low bit constraints. In addition, our method incurs only a small overhead of approximately 16 bytes of the center buffer per crossbar. This demonstrates that even under low ADC precision, it is possible to maintain performance while achieving high energy efficiency with minimal memory overhead. Next, I would like to introduce a work-in-progress research titled Outlier Mitigation by Involved Rotation in LLMs. Since this research is still ongoing, I will focus more on the motivation and problem-solving approach rather than detailed methodology. In this work, we identified the difficulty of the quantizing LLM due to outliers in the activation distributions. Quantization typically map the floating point value to low precision value using a rounded to the nearest based on min-max scaling. However, when a small number of outliers are present, the max value is determined by these outliers, causing most value to be quantized to zero and lose representation accuracy. Two common characteristics of this outlier have been identified in related words. First, outlier appear more frequently in activation than weight. And second, outliers consistently occur in specific channels rather than being randomly distributed. The recent trend to mitigate this issue is the use of a location-based outliers operation. By applying an orthogonal matrix like a Hadamard matrix to input and weight matrix, it is possible to normalize the distribution while maintaining the computational invariance. As shown in this figure on the right, this can normalize the matrix and help suppress the outliers effectively. However, our analysis of the outlier occurrence timing revealed that outlier channels appear after layer normalizations, which exist between transformer blocks. In this figure, these outlier channels are highlighted with red dot, and we observe that their impact become more pronounced after rescaling in layer normalization. This led to us motivation that applying rotation before layer norm is not effective in reducing outliers. The conventional between block rotations are typically applied between blocks, often fused with the output weights of the last layer in the block. However, we found the outlier tend to be emerge inside the block, especially after layer normalization and residual addition. As a result, rotating the input to only cannot effectively suppress these late-stage outliers. That's why we propose in block rotation, which directly target the point where the outlier actually appears. However, changing the rotation position can sometimes amplify outliers even further. To address this, we are exploring a smoothing technique and singular value decomposition to stabilize the distribution using LoRa. Through this approach, the LoRa path is used to process important information in high precision, while the residual matrix is subject to low precision quantization, thereby aim to improve performance. However, further experiment and validation are still needed to verify the effectiveness of these techniques. In a simple experiment, we observed that from the table on the left, the outlier channels significantly impact the accuracy. The proposed in-block rotation method successfully addressed the low bit quantization issue caused by these channels. Despite the overall online computation added to the system, we observed the minimal runtime impact while achieving 30.8 times memory savings. In summary, we addressed the ADC resolution problems by optimizing the weight encoding during training, considering the hardware structure of pin-based accelerators. We also tackled the precision alignment and memory bottleneck issue in LLMs by proposing an in-block rotation to reduce the quantization error in activations. These studies show that ensuring efficient AI operation under constraints such as low power device, limited low memory bandwidth, and real-time processing is not sufficient to optimize hardware or software in isolations. And thank you for your attention. If you have any question.
Okay, this is basically conclude all the four talks given by our presenters. So any questions from before we move forward? Many of you are working on something relevant. Any questions? Apparently, we want to finish this stuff.
At the moment, it's quite difficult or impactful for us to know such large scale models, for example. Digital IoT would be very sort of, yeah, but I'm very more. So I'm gonna probably proceed with those two independently, and we'll try to see like first that that's very important. So that's my current plan. And for your second question, I always feel that the AI field, hardware field, are slowly converging because these days, a lot of ULM related research or Gen AI related research, they draw a lot of inspirations from the computer architecture, especially coding, KB cache, KB cache methods. They're all drawing inspirations from the hardware side. And even the industry, the landscape of the industry is quite similar. So I believe that knowing both sides, becoming the master of both of these will be extremely helpful. Yeah, that's my answer. Yeah. For your question.
Any other questions? Okay, if not, maybe we should move to the next one. So, Han Zheng will be the next one. Well, by the way, I think you log into the room for we share.
Okay. Maybe I should share this.
You should share, yeah. You should share the Zoom. Yeah.
Yeah. Okay.
Okay.
So,
But just for the brief introduction, financial year, our second year, CP student, actually this will be second year in a few days. It's research courses on efficient machine learning with a core emphasis on sparse inference of deep neural network. He will present his work regarding efficient technical review service.
okay. Okay. Thank you for the introduction from Professor. Yeah. Hello, everyone. My name is Han Chunyi, and as the Professor introduced, I'm a second year PhD student advised by Professor Yiran Chen. Today, I will introduce the recent advances in LLM-based multi-agent system. It seems works.
Because no, you turn off one, otherwise.
Oh, I see. Okay, so I will specifically focus on the speeding up the inference of multi-agent systems without retraining the models or changing the serving stack. So the method is called KV-com, which focuses on reusing and realigning the KV caches across agents. We will move from the background and the motivations to the core idea and through experiments and finally give some takeaways. To set the scene, this slide positions ARM agents into the today's landscapes. There are lots of visual taxonomies and frameworks out there. And the big picture is that ARM agents are specialized role that is built on ARMs. And they are often arranged in a team to tackle a complex task. Here we focus on making this collaboration faster by sharing the computation that these agents repeated. Yeah, repeats. Firstly, we want to clarify the definition of the agent and the multi-agent system in our work. For a single LLM agent, it consists of three components. The first is the profile that it contains system prompt template and the serving model and so on. And the second is toolkits that the agent can call. It includes search tools and Python executors and etc. And the third is the memory, which stores memory history and communication history that the agent can refer to. For a multi-agent system, it also contains three components. The first is the agent pool. It is a set that stores pre-designed agents for various tasks. And the second is the dependency graph, which determines the communication paths among agents. For example, who talk to whom and in what order. And the third is the communication protocol, which determines the standard way that pass messages between agents. Yeah, and this figure shows how the same shared text is used in multiple places in such a system. So in a multi-agent system, where does the efficiency get lost? There are two places. The first occurs within agents, where the servers has already reduced KV caches in a common way. For example, they will keep a KV cache of the response text between multiple turns and keeping the prefix KV cache between multiple requests. So this efficiency issue has been well resolved. The second takes place between agents, where the agents usually often share the text of a message, not the KV cache behind it. That is because the different agents will have different prefixes. So naively reuse the KV cache will misalign the positions and the context. So in this case, the agents have to recompute the KV cache from scratch for long and overlapping passages, which can be very wasteful when the repetition times get larger. And the prior works explores various acceleration methods for ARMs, but mostly are within a single model or a single context. And the typical categories can include three paradigms, that is cache reuse, cache compression, and system kernel optimization. For the KV cache reuse, prior works proposed the selective recomputation methods, which focuses on select the sensitive tokens or the critical layers to recompute the KV cache. And for example, in this second column, it is the cache blend method that will pick the high variance tokens for recomputation. And in the third column, it is the droid speak method that will select the most critical layers for recomputation. And these methods are all powerful, yet they assume the KV cache reuse are in a single context or a single model. And they cannot fully support the cross-agent or cross-context KV cache reuse. So because the reason is that the different agents will have different practices, then their KV cache will be different. So under the cross-agent KV cache reuse scenario, how can we reuse KV cache? Now we have the following two motivations. The first is the offset variance problem, which means the same shared text can incur vastly different KV deviations once it is placed in different prefix contexts. In the upper right figure, the blue and yellow lines refer to the key cache and the value cache offset distribution under different prefixes. It can be observed that the key cache offset distribution will be very different under different prefixes. And the second motivation is the offset proximity characteristics, which means the KV cache of two similar tokens prefixed with two different prompts will present similar deviation distributions across layers. We can see this in the lower right figure. The blue and green lines refer to the key cache offset distribution of two similar tokens under the same prefix change. And while the red and the orange lines refer to the value cache offset distribution of two similar tokens under the same prefix change. And it can be observed that the distribution of two tokens, similar tokens, are close in their KV cache offset. And another characteristic in this figure is that by aligning the key cache position, its cache offset distribution will be much smaller than the unaligned version, which is compared between the triangle lines and the dot lines with the same color. So when we analyze the KV cache statistically, we have two patterns that stand out. The first is that token similarity is linked to its KV cache similarity. That means tokens that are closer in the embedding space that will have similar KV cache vectors across layers. And in this upper left figure, we show this feature. In this figure, the key cache distance and the value cache distance between the two tokens are grouped into three groups. And they are near, mid, and far. And for the we can see that under the nearest tokens will have the closest cache distance. Yeah, and the second pattern is about the KV cache offset proximity distribution, which means under the same prefix change, the offset often for similar tokens will stay close. We also visualize these features in the lower left figure. It shows that the most similar tokens in their embedding space will have the closest key cache or value cache offset distribution in the under the same prefix change. So this insight motivates us to store several previous listings cases to use as a reference, which we call anchor. So we can use these previous listing cases to predict or approximate the offset of the new cases. So this insight is the foundation for our KVCOM's design. So how does KVCOM actually work? In one sentence, KVCOM is a training-free prompt adaptive KV cache reuse strategy that will reuse KV caches across agents without changing the model or training, which will first align the key cache position, then bias the placeholder cache KV cache and the prefix segments KV cache via the estimated KV cache offset, which is predicted from the previously seen and the similar anchors And this figure illustrates the overall process of our KVCom. We summarize this process as follows. There are several steps. The first step is the initialization. That means before any user request arrive, all agents will pre-compute and store the KV caches for all prefix segments defined in their prompt templates. And step 2 is the placeholder readiness, which means when a request arrives, each agent checks whether all placeholder space KV caches are available. If not, this will be pre-computed in parallel. And these newly generated placeholder KV caches will then enter the anchor prediction module to check for similar samples in the anchor pool and enable reuse. And step 3 is the reuse or fallback. Once all placeholder KV caches have been generated, and the agent will determine if there are reusable KV cache deviations for each placeholder. If not, then the standard dense prefilling is used. For placeholders without reusable deviations, the agent will compute the difference between their actual and the base KV caches, and then store this deviation in the anchor pool to expand anchor coverage. And step 4 is the offset approximation. That means if all placeholders have reusable KV cache deviations, the agent will fetch the matched anchors, then estimates the KV cache deviations and updates these placeholder and the prefix KV caches in parallel. And at step 5 is decoding. After we approximate the KV cache for all the placeholders and the prefix segments, the agent will combine the updated placeholder and the prefix KV caches to initiate the response decoding. And after the generating a response, we will execute anchor update. That means the response KV cache will pass through the anchor prediction module. If a similar anchor exists, the cache is stored in shared memory for future retrieval. Then this agent will await the next request. If no similar anchor exists, the response KV cache is stored in the anchor pool for dependent agents to fill in the deviations under their respective contexts. Then the agent will await the next request. So this is the overall process of our KVCom in the multi-agent system. And here is a detailed introduction of anchor-based KV cache communication module. Specifically, we will maintain an anchor pool, which will store three elements. In the key of placeholder name, we will store a base KV cache for the placeholder, which is computed under its initial context. And in the key of agent ID placeholder, it will store the placeholder KV cache offset, which is computed by the difference between the base KV and the ground truth KV under the new context for the placeholder. And in the key of agent ID of prefix, it will store the prefix KV cache offset. This prefix segment is the neighboring prefix segment to that placeholder. So and during runtime, we will also predict whether the incoming placeholder segments should be reusable or added as a new anchor, which is based on this function. It contains two criteria. The first item is about the length compatibility. It tests whether in the anchor port there are anchors that is longer than the current placeholder text. And the second term is about the embedding proximity, which measures whether in the anchor port there are anchors that is similar enough to the current placeholder. Here we measure this embedding proximity by the entropy of its error to norm distance on the embedding space. So if there are anchors that is close enough to the current placeholder, then we will reuse these anchors KV cache offset to approximate the current placeholder's KV cache. If not, we will compute once and add it as a new anchor. So when the placeholders KV caches are all predicted as reusable, then KVCom will do two things. First is anchor matching. Here we will quickly retrieve the most similar anchors in parallel for all the placeholders. And this process is much cheaper than the dense prefilling process. And second is the offset approximation. Here we will blend retrieve the offset from the anchors and weighted by the embedding similarity on the embedding similarity, and use this approximate offset to adjust the placeholders and the prefix segments KV cache. And then we will concatenate the updated KV caches to start decoding. So this is a method part, and now we will test how KVCom performed on the GPT-Swarm framework and on 3 types of tasks. For the RAG task, we test on the MMLU benchmark. For the math reasoning task, we test on the GSMFK benchmark. For the coding task, we measure it on the human eval benchmark. And we use 2 open source models. They are Llama 3.18 billion instruct and Q1 2.5 Coder 7 billion instruct models. We ran these models on at the setting of 2 to 5 agents. And we measure three metrics: accuracy, reuse rate, and time to first token, which is also named as TTFT. We compare against the cache blend method, which is the kind of traditional selective recomputation method. And we will show how this traditional selective recomputation method will struggle with varied prefixes. And in this table, the results show that KVCom can achieve superior or comparable performance to the original dense prefilling process. And while the cache blend only perform a modest performance on most benchmarks. Now let's look at the TDFT performance. We, in a 5-agent setup with 1,000 input token and 512 prefix token and 512 output length token. The first agent will don't benefit too much from the KVCom because it has no upstream KV cache to reuse. But for the downstream agents, the TDFT can be speed up by up to 13.7 times faster. And we also varied the prefix length and output length. And then the TDFT speed up can be ranged from 4.35 times to 13 times faster. And so the observation it can be observed that with the prefix or output length become longer, the speed ups performance will be more significant. This is reasonable and within expectation. Let's also check how stable KVCom will be when the request arrives in different orders. In this table, in table 4, we can find that KVCom will be very steady whether the requests come in random order, ascending length, or descending length. That's because the reuse decision is based on the similarity, not the fixed sequence. We also conduct ablation studies to show that all 3 show that all three steps, including position alignment, placeholder KV cache offset, and prefix KV cache offset. All these three components are necessary for a correct approximation. And we can find that remove any one, the accuracy will drop. This confirms that each step's role is very essential in keeping results correct. Now, we also conduct some hyperparameter sensitivity analysis. And here there are two hyperparameters. The first is the entropy threshold gamma. This controls how aggressive we are in reusing those similar tokens, similar anchors, and increasing it will boost reuse to 98% with only a small accuracy drop in the in math tasks. Secondly is the anchor port size V, which determines the maximum number of the stored anchors for each placeholder. When the stored number exceeds this value, we will drop those oldest and the least updated anchors. We can observe that the accuracy will stay stable as we add more anchors, but the reuse rates will improve until 20 anchors. Then it will flatten out. So in our experiment, we set gamma to 0.3 and V to 20. Finally, we want to visualize the detailed response of each agent using different cache alignment strategies. The left is the original response of each agent without cache reuse. The middle part is the responses generated by cache reuse via aligning the position encoding of key caches and offsetting the prefix segments KV cache. So the placeholder KV cache is not conducted in this case. And in the right part, the responses will be generated by combining all three components. It can be observed that although the middle setting eventually outputs the right answer, that is option C, but its reasoning chain is clearly degraded. Yeah. For example, the agent omits a formal definition of decalogue, repeat the keywords from the knowledge expert agent, and make analysis on agents that do not exist, resulting in a logically fragmented discourse. This right answer for the wrong reasons phenomenon underscores that two-level alignment alone still disrupts the causal dependency between evidence, inference, and conclusion. Therefore, the combination of all three alignment processes is essential for achieving a coherent explanation path that is comparable to the original response. So to sum up, these are three main points in this work. First is the problem, which reveals that different prefixes can cause offset variance, making direct KV reuse fail. Second, the solution, where KVCOM is proposed to realign positions and approximate offsets from an anchor pool with no training nor model changes. Third is the results, which can achieve up to 13 times faster TDFT in multi-agent system with high reuse rates and stable accuracy. And that's all. Thank you.
Okay, so hi everyone. My name is Feng Cheng, and today I'm excited to share my work titled Echo, Improving Memory Bandwidth and Capacity for Large Language Models via Entropy-Aware Cache Compression. And this work is published in ISCA this year. So let me start with a quick summary of what this talk will cover. So we will first introduce Echo, our entropy-aware cache compression algorithm tailored for efficient large language model inference. And then I will walk through how we integrated a hardware decompressor and compressor to enable runtime compression and decompression of weights, activations, and KV cache. And finally, I will show how Echo outperforms popular quantization schemes in both accuracy and performance. So the size of AI models have been increasing rapidly in the past decade with the model size growth. Running these language models require intensive data movement for loading weights and intermediate data. Meanwhile, machine learning acceleration hardware has continued to evolve, improving both compute capabilities and memory throughput. However, due to the cost and hardware limitations, memory bandwidth scaling has lagged behind the computation performance and the rapid growth in model size. So as a result, most large language models become memory-bounded workloads, and their inference performance typically scales linearly with the size of model parameters and the intermediate values like KV cache due to the low compute intensity. Using Llama 7 billion model as an example, with a batch size of 8 and sequence length of 1024, we can analyze the arithmetic intensity, which is the ratio of compute to memory access. For JAM, the intensity is only 8, and for the batch JAM, it is even lower, only 1. So both of them are far below the compute efficiency threshold of 200, as shown in the Rooflight model. So in this case, applying compression to this data helps close the gap between the compute and memory, shifting the large language model inference closer to the compute bound region. So in this work, our goal is to design a compression method that retains the most information using fewer bits. Quantization is a fundamental technique in model compression, and to evaluate the effectiveness of different quantization schemes, we introduce two concepts. One is the information entropy to measure the level of information preserved in the quantized data. And another one is the bit overhead to reflect the actual cost of each scheme. So the bottom chart compares the information entropy and the bit overhead of three popular quantization schemes, the tensor-wise, channel-wise, and group-wise. And our proposed entropy-based compression preserves the most information while using a similar base overhead as tensor-wise compression. So in addition to the effectiveness of the compression algorithm itself, in this work, we designed dedicated hardware blocks for decompression and compression to enable faster data processing. The dedicated hardware compressor and decompressor also offload these operations from the SIMD data paths on GPU. Also, to ensure efficient access through memory hierarchy, we design comprised data block size perfectly aligned with the memory hierarchy. We designed the target comprised block size to align with the GPU cache line and memory transaction block size, typically between 32 bytes and 128 bytes. So in this design, we choose 64 bytes as the comprised block size to strike a balance between minimizing hardware overhead and maximizing bandwidth utilization. So for target compression ratios, we choose powers of 2 to simplify the alignment. We use 4-time compression for race and KV cache and 2 times compression for activations to get optimal balance between effective data compression and model performance. So now let's look at the Echo model compression algorithm. We first group weights and activations into chunks of 128 elements, then normalize each group using its own scale to ease the quantization. And then the k-means clustering is applied within each group to replace the values with centroid indices. preserving structure with reduced precision. We then perform cross-group k-means to enable a shared codebook, so that we can reduce the metadata and improving reuse. And quantized values are assigned using round to nearest, generating compact integer representations. Finally, we apply the Huffman coding to comprise the frequent values more efficiently, and finally pad and clip the data to 512-bit blocks. To implement the compression scheme in hardware efficiently, we address several challenges. First is that Huffman codes generally have variable length. So long codes require more complex logics to compare during decoding, and short codes, it needs more buffering due to the coding process increasing memory pressure. We observe that most codes fall within the 2 to 8-bit range. So we constrain all codes to this range and to simplify the hardware logic and ensure efficient implementation. The second challenge is that selecting the right k-means pattern for each KV cache data at runtime is costly. We observe that most patterns, they are highly skewed with noticeable differences between their minimum and maximum values. So we simply compare each group's minimum and maximum values to those candidate patterns for fast selection. The lightweight check turns out to reduce the selection overhead dramatically. The third challenge is determining how many patterns and codebooks are required. If too few, the model quality suffers. If too many, and we lose efficiency. We address this through a design space exploration and find out the sweet spot, the 4 shared k-means patterns and 4 Huffman codebooks per pattern, achieving a strong balance between compression efficiency and accuracy. Now comes the cache compression framework. So our design places the decompressor between the SM cores and L2 cache, and the decompressor between the L2 cache and HBM. This reduces the total data traffic to DRAM while delivering high precision data to the SM cores for direct compute. The decompressor sits between the L2 cache and L1 cache, decompressing ways or activations for the SIMD compute. It first fetches the metadata, including the k-means patterns, Huffman codebook, and signal factors, and then perform parallel Huffman decoding using 64 decoders per compressed block. So the decoded indexes are mapped back to FP16 values via the shared codebook with outliers reinserted as needed. So the result is fully restored into an FP16 tensor ready for computation. And for compressor, it is placed between the L2 cache and the memory, reducing the KV cache and activation size to memory. So it selects the k-means patterns through the minimum and maximum value comparison, and detect outliers with a parallel sorter and run parallel Huffman decoding. Then the compressed data are packed into fixed length blocks. So this process is fully parallel and pipelined to meet hardware throughput requirements. Now comes the evaluation part. We compare ECHO with other popular compression schemes like AWQ and Quarot on variable llama models and Mistral, and we achieve the state-of-the-art perplexity here. And we also compare the inference performance during decoding. We compare ECHO on Llama and Mistral on different batch size, sequence lengths, and on different batch size and sequence lengths. So the result turns out that our ECHO method can outperform existing state-of-the-art approach by 2 to 3 times. And that's it. Thank you. Questions?
Okay, we probably have very quick Q&A, so any questions? This paper published in July East, so a little bit more than a month ago. Please.
I have a question about the KV short computation. Because I was just wondering if there what the agents are agents are deployed at different machines.
The other experiments is on the same.
Oh, it's on the same machine. I see that, because I was thinking, there again, agent over.
Yeah, Asian work at the. It can be something that currently a lot of certain programs like they have all the distributed.
Got it, thank you.
Right, another question? Okay, so no more questions, and we just, maybe just conclude here, so let's start. These are six, yeah. Okay, so talk about for coming, talk about for the dual armor.
我感觉有点问题。我全给我发消息了，声音